Now, chapter 3, exercise numericals. Example 3.1. The storage battery of a car has an EMF of 12 volt. If the internal resistance of the battery is zero point 0.4 ohm, what is the maximum current that can be drawn from the battery? Now, we have the EMF 12 volt, internal resistance of the battery, that is zero point 0.4 ohm. Now for the current, we have the equation I, that is equal to E upon R plus R. Now to obtain the maximum current from the battery, from this equation we can say if this R, the resistance in the external circuit, that is equal to 0, then current drawn from the battery, that will be maximum one. So for R equal to 0, I, that will be maximum one. So we can write I, that is equal to I maximum, that is E by R. Take R equal to, capital R equal to 0. So 12 upon zero point 0.4. So 30 ampere, that is your answer. Clear? 3.2. A battery of EMF 10 volt and internal resistance 3 ohm is connected to a resistor. If the current in the circuit is 5 ampere, what is the resistance of the resistor? What is the terminal voltage of the battery when the circuit is closed? Now see, EMF of the battery, that is 10 volt, and its internal resistance, that is given to you 3 ohm. Current I in the circuit, that is 0.5 ampere. And now we have to calculate the resistor in the circuit connected one and the terminal voltage of the battery. Now we have the equation for the current in the circuit, that is I equal to E upon capital R plus small r. So we can write capital R plus small r, that is equal to E upon I. So capital R, that is equal to E upon I minus small r. Now substitute the values given to you. E, that is 10, I, that is zero point 0.5, R, that is 3. And now solve this one. You will get R, that is equal to 17 ohm. Now we have to calculate terminal voltage. So terminal voltage V, that is equal to IR. So we can write I, that is 0 0.5 into 17. So that is 8.5 volt. Clear? Here you can calculate the terminal voltage using equation V equal to E minus IR also. Say E, that is 10 volt, I, that is 0.5 ampere, internal resistance, that is 3. So again you will get the same answer. Terminal voltage, that is 8.5 volt. Clear? 3.3. A 3 resistors 1 ohm, 2 ohm and 3 ohm are combined in series. What is the total resistance of the combination? B. If the combination is connected to a battery of EMF 12 volt and negligible internal resistance, obtain the potential drop across each resistor. Now see, 3 resistors given to you. R1, that is 1 ohm, R2, that is 2 ohm, R3, that is 3 ohm. Now for series combination of 3 resistors, we can write the equation for the equivalent resistance, that is equal to R1 plus R2 plus R3. So that is 1 plus 2 plus 3, that is 6 ohm. Okay. Now current flow in the circuit, I, that is equal to V upon R equivalent. Supply voltage, that is 12 volt. and equivalent resistance we calculated of the circuit, that is 6 ohm. So 12 by 6, that is 2 ampere. Now we have to find the potential drop across each resistor. Now this is the series combination. So current through each resistor, that will be the same one, I. So potential drop across each resistor, that is, for first one, V1 equal to IR1, so that is equal to 2 into 1, that is 2 volt. For second resistor, V2 equal to IR2, that is equal to 2 into 2, that is equal to 4 volt. For third resistor, V3 equal to IR3, that is equal to 2 into 3, that is equal to 6 volt. And see here, V1 plus V2 plus V3, that is 2 plus 4 plus 6, that is 12 volt. That is the total supply voltage. Clear to all of you? 3.4. A three resistors 2 ohm, 4 ohm and 5 ohm are combined in parallel. What is the total resistance of the combination? B. If the combination is connected to a battery of EMF 20 volt and negligible internal resistance. Determine the current through each resistor and the total current drawn from the battery. Now see, supply voltage, that is 20 volt. Three resistors are given to you. R1, that is 2 ohm. R2, that is 4 ohm. R3, that is 5 ohm. And all these are connected in parallel. So equivalent resistance in parallel combination 1 upon Rp, that is 1 upon R1 plus 1 upon R2 plus 1 upon R3. That is our equation. So we can write 1 upon Rp, that is 1 by 2 plus 1 by 4 plus 1 by 5. So resultantly you will get 1 upon Rp, that is 19 by 20. So Rp, the equivalent resistance of the parallel combination of these three resistors, that is 20 by 19 ohm. Clear? Then after, we have to find the current through each resistor. Now this is the parallel combination. In parallel combination, the potential difference across each resistor will be same one. And that is equal to the supply voltage of the battery, 20. So current through first resistor, I1, that is V by R1. So V, that is 20, R1, that is 2, that is 10 ampere. Then current through second resistor, I2, that is V by R2, that is equal to 20 by 4, that is 5 ampere. Current through third resistor, I3, that is equal to V by R3, that is 20 by 5, that is 4 ampere. So total current drawn from the battery, that is the summation of these three currents. So total current in the circuit, that is I equal to I1 plus I2 plus I3, that is 10 plus 5 plus 4, that is 19 ampere. Clear? 3.5. At room temperature 27 degrees Celsius, the resistance of a heating element is 100 ohm. What is the temperature of the element if the resistance is found to be 117 ohm? Given that the temperature coefficient of the material of the resistor is 1.7 into 10 raised to minus 4 degree Celsius. Now see here, the reference temperature T0, that is 27 degrees Celsius, and at 27 degrees Celsius the resistance, that is 100 ohm. So we can write resistance at temperature T0, that is equal to resistance at temperature 27 degrees Celsius, that is 100 ohm given to you. At some temperature T, the resistance is 117 ohm given to you. And the temperature coefficient, that is alpha, equal to 1.7 into 10 raised to minus 4 degrees Celsius. And you want to find that temperature. Now we have the equation R at any temperature T, that is equal to R at reference temperature T0 into 1 plus alpha T minus T0. So substitute the values. R at temperature T, that is 117. R at temperature T0, that is 100, into 1 plus alpha, that is 1.7 into 10 raised to minus 4 into T minus T0, that is 27. So take this 100 on left hand side. So 117 by 100, that is 1.17, that is equal to 1 plus alpha, that is 1.7 into 10 raised to minus 4 into T minus 27. Take this one on left hand side. So 0.17 equal to 1.7 into 10 raised to minus 4 into T minus 27. Now make T minus 27 as a subject of equation and solve it. You will get the resultant answer T in terms of degree Celsius. Clear? 3.6. A negligibly small current is passed through a wire of length 15 meter and uniform cross section 6 into 10 raised to minus 7 meters square. And its resistance is measured to be 5 ohm. What is the resistivity of the material at the temperature of the experiment? Very simple thing. Length, that is 15 meter, area of cross section, that is 6 into 10 raised to minus 7 meters square. Resistance, that is 5 ohm. Resistivity that you want to calculate. We have the equation for the resistance, that is R equal to rho into L by A. So rho, that is equal to R A by L. So we can write the resistivity rho, that is equal to, now R, that is 5, A, that is 6 into 10 raised to minus 7 upon L, that is 15. Solve it, you will get the answer. Clear? 3.7. A silver wire has a resistance of 2.1 ohm at 27.5 degrees Celsius and a resistance of 2.7 ohm at 100 degrees Celsius. Determine the temperature coefficient of resistivity of silver. Now, resistance at 27.5 degrees Celsius, that is the reference temperature, it is 2.1 ohm. And resistance at 100 degrees Celsius, that is 2.7 ohm. And what is alpha that we want to find? Very simple. Resistance at temperature T, that is resistance at reference temperature T0 into 1 plus alpha T minus T0. This is our equation. Now we can write temperature T, that is 100 degrees Celsius. So R at 100 degrees Celsius. Reference temperature T0, that is 27.5 degrees Celsius. So R at 27.5 degrees Celsius into 1 plus alpha T, that is 100, T0, that is 27.5. Substitute the values. So R 100, that is 2.7, R at 27.5, that is 2.1 into 1 plus alpha into 100 minus 27.5. Now, take this 2.1 on left hand side, then 2.7 upon 2.1, that is equal to 1 plus alpha into, this difference is 72.5. Now, make alpha into 72.5 as a subject. So alpha into 72.5, that is 2.7 upon 2.1 minus 1. Then after make alpha as a subject of equation, you will get the answer. Clear? 3.8. A heating element using nichrome connected to a 230 volt supply draws an initial current of 3.2 ampere, which settles after a few seconds to a steady value of 2.8 ampere. What is the steady temperature of the heating element if the room temperature is 27 degrees Celsius? Temperature coefficient of resistance of nichrome averaged over the temperature range involved in. is 1.7 into 10 raised to minus 4 degrees Celsius inverse. So initially, when the circuit is switched on, the current is 3.2 ampere. At that time, room temperature is there. So we can say it is a cold wire, but when the current flows through it, wire will be heated. So its resistance increases, voltage is constant, so current decreases, and finally, at a certain temperature when it is heated, the current becomes a steady one, right? So when the current becomes steady, at that time, what is the temperature of that wire that we want to find? Simple thing. Now voltage, that is 230 volt, initial current I1, that is 3.2 ampere, then final steady current, that is I2 equal to 2.8 ampere, initial temperature T1, that is 27 degrees Celsius, T2, that is what? Alpha, that is given to you 1.7 into 10 raised to minus 4 degrees Celsius inverse. Now resistance at temperature T2, that is equal to resistance at temperature T1 into 1 plus alpha T2 minus T1. Now resistance at temperature T1, so that is initial resistance, that we can write voltage upon initial current. Then resistance at temperature T2, that is voltage upon final current I2. So we can rewrite the equation RT2, that is V upon I2, that is equal to R at T1, that is V upon I1 into 1 plus alpha T2 minus T1. So V cancelled. Take this I1 on left hand side. So I1 upon I2, that is equal to 1 plus alpha T2 minus T1. So I1, that is 3.2, I2, that is 2.8, that is equal to 1 plus alpha, that is 1.7 into 10 raised to minus 4 into bracket T2 minus 27. So 3.2 upon 2.8 minus 1, that is equal to 1.7 into 10 raised to minus 4 into T2 minus 27. Now solve this one, make T2 as a subject of equation, you will get the answer. Clear to all of you? 3.9. Determine the current in each branch of the network shown in the figure. Now see, this one is the network. See here, 10 by 5 is not equal to 5 by 10. It implies that the network given to you, that is like Wheatstone bridge, but it is not balanced one. So definitely from this middle branch, some current is flowing. Now suppose here the current drawn from the battery of 10 volt, that is I ampere. When it entered to this junction A, now it is divided in two parts. Current I1, that is in the branch AB, and current I2, that is in branch AB. Now from B, suppose I3 current is in the branch B2D, means B2C, I1 minus I3 current will flow. Now I2 current enter to D, this I3 current enter to D, and when both leave D, then D2C branch will give you the current I2 plus I3. And finally, when I1 minus I3 enter to C and I2 plus I3 enter to C, and when it leave, here we'll get resultant current I. Clear? Now we have to find all these currents in each branch. Means we have to find I1, I2, I3. This type of one illustration we solved. See, first consider the loop A, B, D, A. So A to B in the direction of current, so minus 10 I1. Then B to D, again in the direction of current, so potential difference minus 5I3. D to A, so in the opposite direction of current through resistor 5 ohm, so potential difference across it, that is plus 5I2, that is equal to 0. This is equation 1. Then consider the loop B, C, D, B. So B to C, you are moving in the direction of the current I1 minus I3 through 5 ohm. So potential difference is negative minus 5 into I1 minus I3. Then C to D, you are moving in the opposite direction of the current. So potential difference across 10 ohm, that is plus 10 into I2 plus I3. Then D to B, you are moving in the opposite direction of current I3. So potential difference across 5 ohm, that is plus 5I3, that is equal to 0. Now simplify this one. So finally, in terms of I1, I2, I3, your equation minus 5I1 plus 10I2 plus 20I3, that is equal to 0. Now consider the loop A, B, C, D, A, this outer one. So A to B in the direction of current, so potential difference minus 10I1. B to C in the direction of the current, so minus 5I1 and plus 5I3. Then C to D in the opposite direction of current, so plus 10I2 plus 10I3. Then D to A in the opposite direction of current, so plus 5I2, that is equal to 0. So resultantly you will get the equation minus I1 plus I2 plus I3, that is equal to 0. Now solve these three equations by elimination method and then find out I1, I2, I3. So I1, I2, I3 are the currents in branch AB, AD and BD. Then current through BC, that is I1 minus I3. Once you have I1 and I3, then you will get this one also. Then current through branch DC, that is I2 plus I3. Once I2 and I3 is calculated, you will get current in the branch DC, that is I2 plus I3 also. Clear to all of you? 3.10 A. In a meter bridge, say figure, the balance point is found to be at 39.5 centimeter from the end A, with resistor Y is of 12.5 ohm. Determine the resistance of X. Why are the connections between resistor in a Wheatstone bridge or meter bridge made of thick copper strips? Then B. Determine the balance point of the bridge above if X and Y are interchanged. C. What happens if the galvanometer and cell are interchanged at the balance point of the bridge? Would the galvanometer show any current? Now see here. The balancing point initially you are getting at length L1, that is 39.5 centimeter. So at that time your L2, which is 100 minus L1, so that is 100 minus 39.5 centimeter. So that is 60.5 centimeter. At that time resistance Y, that is 12.5, and what is X that you want to calculate. Now here see in this circuit actually consider this R as X and S as Y. Okay. So X upon Y, that is equal to L1 by L2. So X equal to L1 by L2 into Y. L1, that is 39.5 upon L2, that is 60.5. Y, that is 12.5. So you will get X, that is equal to 8.16 ohm. Now if X and Y are interchanged, then Y by X that we can write equal to L1 dash upon L2 dash. But this L2 dash you can write 100 minus L1 dash. Now Y that is 12.5, X we already calculated 8.16. Now L1 dash upon 100 minus L1 dash equal to 12.5 upon 8.16. From this one, you can calculate L1 dash also. Means after interchanging X and Y, you will get the balance point at L1 dash. You can calculate it from this one. Now here it is asked you, why are the connections between resistors in a Wheatstone bridge or meter bridge made of thick copper strips? These are the thick copper strips. Because if the copper strips are thick one, then their resistances will be negligible one. So it will not affect the balancing point. Then in question C, it is asked what happens if the galvanometer and cell are interchanged at the balance point of the bridge. It doesn't make any difference to the balance point because you have to connect between two terminal, the galvanometer, and between another two terminal which are diagonally opposite. In theory, we discussed this thing, the battery. So if we interchange, then also the balancing condition that will remain the same one. So there will be no change in the null position or balancing position. So if the balancing position remains the same one, means the bridge remains balanced one, it implies that through the galvanometer, no current will flow. Clear to all of you?